Welcome to my talk, You Shall Not Pass, Analyzing an NSO Spyware Sample. It's a pleasure and it's an honor for me to be able to stand here on the stage at Black Hat. My name is Matthias Frielingsdorf and I'm the VP of Research at the company iVerify. My main research directories are iOS malware and mobile device security in general. On September 7th in 2023, Apple released a kind of emergency patch for iOS 16.6.1, closing two specific vulnerabilities which have both been exploited in the wild. One of those vulnerabilities, the first one, got pretty famous just a couple of days later, and it was called the WebP vulnerability. On the same day, CitizenLab published the latest research about the Pegasus BlastPass exploit chain. On this specific sample, NSO used a PassKit attachment which was delivered over iMessage to infect iPhones with a zero-click exploit chain. The specific target here was a person working for a Washington, D.C.-based civil society organization, and the exploit was found during a routine forensic analysis that has been done on the specific device. The attribution was made to NSO. There is a couple of other BlastPass reports which are available, our own blog, which is featuring a preview for this specific talk, and then once again, there is also another report which has been done by Amnesty International about the sample. Today, I'm not going to reveal any more 0 days, and I'm also not going to leak any weaponized sample of this exploit chain. But we're going to go on a journey on how we've discovered and analyzed the latest sample of NSO's Pegasus exploit chain. What I want you to remember about today is that detecting iOS malware with forensic analysis is possible, and I'm going to show you the steps which are necessary to unveil the final payload of the sample. And we're going to discuss some more specific indicators of compromise for this specific sample which haven't been discussed in public before. So this means we're starting right now here on this little map, and the only thing that we have is our knowledge about this BlastPass sample. Last year in October, a customer reached out to us, and they told us that they found a potentially compromised device. So if a customer reaches out, we're usually trying to do a forensic analysis on the specific devices. So that means the customer gave us some data sources in this particular case. We got access to crashlogs, an iTunes backup, and some telemetry data. Then you're using normally a couple of tools. For crashlogs, you have manual scripts that you can do. There's not a well-known tool already available. But for an iTunes backup, you can resort back to MVT, which is the mobile verification toolkit, which is developed by Amnesty and the de facto standard for analyzing iTunes backups for compromises. And for telemetry data, you revert back to scripts. But what are we trying to do with these data sources? So in the essence, we're looking for examples of suspicious activities. This could be a process which is starting from private var temp. It could be a process that is doing network calls, or a process that is running with elevated privileges such as root. Additional indicators of compromise are files that have been written to disk, or if a process crashes repeatedly. And the first glimpse that I'm normally doing is I just scroll through the list of available crash logs. And then in this particular case, there was one pattern which was pretty obvious. So we had a couple of home D crashes, which were about 25 times. Then there was a little break, and then afterwards we had 35 MessagesBlastDoorService crashes. And MessagesBlastDoor is in particular interest here because the CitizenLab report was named BlastPass, and MessagesBlastDoor is the service which is responsible for unpacking iMessage attachments and to make sure that those are rendered safely. So this is suspicious. And that means we should take a little bit deeper look. So if we're looking at the first home D crash, what we can see is, of course, the name of the process. We can see this particular device is running iOS 16.6, and 16.6 was still vulnerable for BlastPass. And then we could see also that this process is just crashing with a normal SIG abort. At this time, I was believing that this particular crash was actually not part of this exploit chain, but it resolved to another exploit chain, which is called Pwn Home, which was valid until iOS 16.1.2. So it looked to me pretty obvious that the attacker might have been just tried to use an old exploit. This failed at first, and then they changed to the newer exploit, so not burning any new chains. If we're looking into the MessagesBlastDoorService crashes, we can see that the exception type is already much more severe because this is a bad access and it's a kernel protection failure at a specific memory address. So something was clearly going wrong. If we're looking into the thread that actually crashed, what we can see here is that on line 6, 7, we started to see that there's an NSK archiver which was decoding a couple of objects. And if we're scrolling down on this one, we can see that this goes up to line 510. So this has to be a very, very large keyed archiver which has been archived, or maybe something is clearly wrong with the sample. For me, that's suspicious as well. So I had a couple of crashes which were all going on specific time frames. This is a perfect starting point if you want to look into an iTunes backup for further analysis. And if you're quickly checking the backup at this specific point in time, we also saw that there's a couple of there's a process, IM transfer agent, which did a couple of network calls. This process is responsible for downloading iMessage attachments. So this makes sense if we have a MessagesBlastDoor crash and we have a process which is downloading an attachment before. But the question is, can we also see that specific attachment in the data? And yes, we can. We can see that there is a sample.pkpass file which has been downloaded 8 times. It could be all the same sample, it could be different samples that have been downloaded. We don't know that yet, but we do know we have this specific mention in 3 times. This is very suspicious as well. But the golden question, are those files actually in the backup? And yes, they are. So at this point, we're mostly done with a certain state of forensic analysis because we've already found a specific sample that is interesting for us. So what we're doing next is now trying to figure out what is a PKPass sample first. And there's an expert that we, since probably last year, can always ask, which is always a good choice. We just asked ChatGPT. And the actual response that we get here is not that off or wrong. So it tells us at the second paragraph at the bottom that a PKPass file is actually, or essentially, a zip archive. And it contains a couple of JSON files. Well, of course, we always should validate. So let's check it with file. And what we can see here, yes, indeed, it's a zip archive. And the zip archive is roughly 175 kilobytes large. So let's archive it and see what's inside of this. If we look inside, we find a couple of JSON files, as predicted, but we also find a file which is a logo.png that directly stands out. And that's not only because it has like 5.8 megabytes of a size, which is quite a lot. So that logo is definitely huge. If we file again, then we can see that this logo is actually not a PNG file, it's a WebP file. And this is where it gets really interesting because this ties us back to the WebP vulnerability that we've talked in the very beginning. This particular vulnerability is not really solved yet. And there's already a lot of talks that have been going on here. And I'm not going to add any more details to the specific vulnerability today. But I do want to make at least a little bit of note that there is an upcoming talk by Ian Beer who is probably going to talk a lot about the specific vulnerability and is uncovering a couple of the unknown questions at the moment. Now let's take a closer look at the sample. And what is usually the best tool for malware analysis? This is very obvious. Of course, it's strings. So if we run strings on this, what we only get is a couple of A's. So that's not really helping. But maybe we should have started to look at the very beginning of this file. And if we look at the strings here, there's 2 things that directly stood out to me. The one is there's a binary plist which is embedded in this file. And the other one is there's a couple of functions in the bottom. And of course, there's a couple of different strings, like an NS call stack array, like DL open, memcopy, so on and so forth, that you would never expect to see in a PNG file or even in a WebP file. OK, so we definitely need to investigate further. At this stage, I could have gone multiple ways. So I could have decided to look more into the WebP vulnerability, how it was constructed of. But I was more interested in getting to that stage where the NS expression is and working on this binary plist file. So let's extract this plist file. It took me a little bit of try and error to get this actually fully extracted, and it was not fully clear if the binary plist is actually just starting somewhere in the file and it goes to the complete end, or there is some other part at the end which is not belonging to that. But in the end, if you do it with DD, it works pretty well, and you get to a BP list. Now, what's a BP list and how can we read it? And once again, ChatGPT is a very good help here. We have two tools which are very good for that. Let's start with PLUtil. If we start here directly at the beginning of the file, what we can see is once again, another, like a lot of A's. And then if we go to the bottom, we can see that this specific BP list has like 113,000 entries. This is not really helpful for analysis. So let's see if plist body itself does any better. Here we can already see that there's a couple of dictionaries and NS arrays which are contained in the specific plist file, but there's a lot of unprintable data as well. And at the very bottom of the file, we can see there's even more of that. This is not going to help us here. We need to understand this a little bit better. So binary plists are very often something which is called an NSQ archiver. And this is a concept which has been used in iOS and macOS very frequently. And this is essentially a method of serialization and deserialization of data. And NSQ archivers, they will always start as a root object. And at this root object, you have a couple of objects which are lying like basically inline below it. Those objects can be an array, a dictionary, an integer, a string, or any other kind of complex object structure. And those objects itself can then include other arrays, other dictionaries, or other objects. But all of those objects are essentially back-referenced back to those first objects that we have in line. So this makes it actually very easy for us in this particular analysis, because the only thing that we need to care about is all those top-level objects. And that means it's time for some Python magic. So what we essentially want to do is import your favorite NSQ archiver lib, read and understand the code a little bit, set some breakpoints, and essentially just replace array objects and dictionaries with their top-level keys, and do not recursively go through the file. And at the end, you print the result, and it should be all. So if we do this, what we're getting back is essentially a structure which looks like that. So we can see a couple of the objects. And if we go to the end, we already see that we're down to parsing objects, which is like at the end of reference 263. So are we better off here? Yes, we are, because we're down to 264 individual objects that we need to analyze. And then afterwards, we can figure out the structure. So let's look at a couple of those. And one of the first ones, which is in particular interest, is object reference 8. And this one starts with a reference to 9. Then you have a lot of references to 10, which are repeated. Then you have 15 times object reference 11, 10 again, 11, 10, 11, and then at the end, you're there. So 11 seems to be important. So let's give this a closer look. And inside of 11, we can actually see that we once again see our NS expression, the function. OK, this is good. That's our payload, essentially, at the end. If we're looking at some of the other interesting ones, we can already see here that we have another object reference to a lot of A's. And then we have another one for a little bit less A's. Still quite a lot. What makes it a little bit interesting here is that because you have all those A's, and this is something which has been used in every single basic exploitation class. If you're trying to exploit a buffer overflow, you fill it up with A's until you know that you can essentially compromise the stack pointer or the return pointer, and then you know where you are in memories. So this is whatever people tell you at first, always put this A's on. So it seems to be that the people who are writing this exploit for NSOs are still sticking to this primitive. They could have used some whatever random string. They didn't have to use A's. But apparently, this is still the thing. So essentially, you could have detected the samples if you would have unpacked it and just looked for 15, 20, 25, or even 250 A's in common. And probably this is not the last time we're going to see this even in weaponized exploits. Object reference 259 then contained another times the payload. So if we sum this up, our payload 11 was used 2 times by objects 8 and 259. 259 was referenced by 242, and then it gets back to the top level. So this is great. So we only know that the only object reference that we need to take care of is essentially object 11. So let's inspect that payload. The payload itself is structured, and I'm making this very easy here, is you have some binary data at the very beginning, which is a couple of bytes. Then you have a couple of bytes, and then you have the embedded strings that we've already seen. This is followed by the NS expression. Some bytes later and some strings again, and then at the end it closes with a lot of null bytes. And then everything else just repeats exactly like the first half. But of course, the remaining questions are, what do all these sections actually do? And what I focused on here is, once again, the NS expression. So we've uncovered the payload right now until the specific step. And once again, of course, we can go into different branches. And I took the branch of just looking at the NS expression. But what is an NS expression itself? And if we're looking at Apple's documentation, we can see that Apple is designing this essentially as a function. This allows you to filter arrays or searches or sorts. The overall, or like the larger category of that, is called an NS predicate. And those NS predicate can have those NS expressions which allow you to execute certain logic operations. So essentially, you have this function call. Then you have a receiver, a selector name, and an argument. And let's look at an example. So you can have a string which is developer tools otest, and then you have the selector which is named LastPass component, and this should resolve then into otest, which is the LastPass component of the string. And that's in a very essential how those NS expressions are built up. If we're looking at the structure of this payload, and I'm a bit sorry because this is so small, but it's going to get better. What we can see here is we have a couple of casts to NSThread and the NSThread.class. Then we have a couple of references to a dictionary where different parts of payloads are going to be stored, and I'm calling those payload CS, payload C, and payload X because they are stored in the keys for the dictionaries X, C, and CS. And at the very bottom, we have a larger payload, which is the one that is executed first. But there's a first question that we need to answer. Why is this still possible? And I honestly don't know. In iOS 15.1, Apple introduced a mitigation that should prevent any of those specific casts for classes like NSThread to still be able to execute. INB already introduced in a talk about NS expression that those mitigations are only implemented by a specific flag, which is set like to false in memory. So that means if NSO found a way to set this flag back in memory with a memory corruption back to 1, they can execute those classes again. But I haven't found any specific evidence on this exploit sample yet. But like I said, I didn't go in much detail about the specific corruption that has been going on. If you're looking at the slide deck when you download it later on, you will find a lot more references to NS expressions and how they have been abused in certain exploits before, because it's not the first time we've seen that. In forced entry, there was another NSO exploit which used already NS expression. Then there is a great talk by INB at last year's OBTS about a sandbox escape in WebKit, which used this as well. And there is a great talk by Austin Emmett at last year's Black Hat about how you can use NS expression for exploitation. And I don't think this is going to get away, so it's a perfect time, if you're interested in that, to just looking some of this up. OK, so let's get back to it. And let's talk about this first executed payload. And let's look at it in a little bit more detail. So the structure that we can see here is that this is essentially a large base64 encoded string. And so why don't we be naive and just try to do this? and this is not working. And why? Because I've overlooked that this specific sample is still using a little bit of compression methods. So we need to do this decompression first, and we need to understand how this works until we can actually decode it. And let's not be naive too. So we already used our expert for a couple of things. And why don't we try to do this once again with an NS expression? And here's the interesting thing, because large language models are very great at taking languages and translating it into other structured languages. This is a good opportunity to just try this out if they can actually turn an NS expression and turn it back into Objective-C code. So I just basically cut out the payload, I put the old NS expression in, and I put it into ChatGPT and asked it if it could transform it. And yeah, it did a pretty good first response. It wasn't perfect, but the only question that remains is, does it work? And yes, it does. So if we're looking at the then decompressed string, what we're getting back to is essentially another very, very large NS expression. And this was so large that it was just not easy readable if you just tried to go through it. So it's time again for some more Python magic. And if we do this, we result to a nicely formatted NS expression that we can start to go through. This one had actually 2,530 lines of formatted NS expression. This is going to be fun. Okay, let's look at a couple of the first lines that we're seeing here. One of the first things that this NS expression did is actually load another framework. And they're loading a framework which is called the Office Import Framework. And this Office Import Framework contains a very specific object which is called an OC mapper. And this OC mapper has a very nice functionality because it has always a mapper for the current thread. So that means this object is always going to be the same if you're still executing this in the same thread. And this is perfect if you want to store something and use variables and NS expressions. NS expressions itself doesn't allow you to do any kind of variables to do computing. But if you have a dictionary that you can always refer to, you can store something in this dictionary with a key, and then you can get it back and you can do computations on it. And we're going to see that in every part of the specific NS expression. You can see the store value at the very bottom, and you can see that this is used again on the next lines for computations. To be able to add or subtract something, they're going to use something which is called NS predicate utilities, which allow you to do some very, very basic calculations. And then directly in the next lines, what we can already see is that they're starting to decoding some of those other payloads that we've seen on the first slide. So this one seems to be, once again, a base64 encoded string. And then they're storing this one in another variable in the dictionary. And then afterwards, they're using plist deserialization to get to the unpacked part. OK, so that also means that payload CS is a plist. That's interesting. So let's try to decode it once again. And that didn't work. We forgot something. And if we look back again at the overall structure of the payload CS in the very first slide, what we can see here is that this payload is base64 decoded, but it also has something which is called a cut decompression, and then once again it uses some AAF base64 decoding. I have no clue what this is. So what's AAF to base64 decoded data? And this time I didn't revert to ChatGPT, but I just wanted to find out if Google knows anything about this. And they don't. So second try, what about cut decompressed data? Maybe we're a little bit more lucky here. And we are. So we can already see that we have one specific hit, which is on GitHub in the core foundation framework. OK, that's good. Why don't we just try this then once again, and let's search on GitHub also for AAF to base64 decoded data. And if we do this, we get a couple more hits, which once again refers to another framework that is used. I could have made my life so much easier at this specific point, because think about it. This specific NS expression is executing in a process. So that means that this specific NS expression is only able to execute functions which are available in this process. So that means if I would have just taken the MessagesBlastDoor sample, BlastDoor service process, and I would have looked at all the libraries which are potentially loaded into it, I could have very easily just found one of the potential libraries where this is it and just inspect those. Okay, but why go the easy way if you can do it hard? Okay, now let's import these frameworks and let's try again. And then we're getting to the binary plist. We can already see there's a couple of tags inside of that, which is very nice. And then we can have a very closer look at the specific plist file. And if we also do the property list deserialization, we're getting to a very nicely structured dictionary where we can actually see that there's like an iPhone model, there's a couple of references, and on those references then you have a couple of variables with some integer values to it. Okay, so these integer values look like some kind of help for computation or some potential memory offsets. And some of the interesting things here is what we could see is there's no reference to any kind of iPads. So either this exploit is not valid for iPads at all, or they have a completely different exploit. And it's also only valid between iOS 16.4.1 and 16.6. So anything later is actually not in this config file. This is great. Now, we have 2 of those payloads already done, and we have 2 to go. So let's look for payload C. And we can see that payload C is mentioning in our first initial payload in lines 99 to 115. It's using a slightly different compression format, and it's also, once again, uses property list serialization. So this should be pretty easy to decode that, and we can also see in the overall structure at the very beginning that it's using the same kind of AF and cut decompressed, and once again AF compression method that the previous sample payload CS used. So if we're decoding this, then we get once again a property list, and this contains another NS expression. And this another NS expression has another payload which is inside the payload C. Okay, so we have a compressed payload which is inside compressed payload C. If we decompress this compressed payload inside compressed payload C, we're getting into compressed payload inside compressed payload inside compressed payload C. And if we do this, once again, we're getting into compressed payload inside compressed payload inside compressed payload inside compressed payload C. But then actually it stops. So after we have decompressed the last one, we're actually down to a very, very end where we only have like one remaining NS expression. Great. 3 are down, 1 to go. But there is no mentioning of payload X in neither payload or in any of the payload Cs and the subsequent payloads in it. We probably forgot something. And what we forgot is that there is another payload which is inside our initial payload at the very, very bottom of this file. The compression for it is something that we already know about, so we just have more payloads to do, but hopefully this one gets a little bit easier. And yes, indeed, if we decompress this, we just get one very nicely structured NS expression. And what we can see here is there's a mentioning of payload X at the very, very bottom of it. Great. This is perfect. Unfortunately, not at all. Because this specific payload is AES encrypted. And even though there is the variable which is in the key, which has a specific entry in our dictionary, if we're trying to follow this variable through the whole NS expression, we don't have any specific mentioning of the key. So there's no key in clear sight. Probably the key is somewhere else in this whole payload, or maybe the key is downloaded from the internet. I don't know this yet. This leaves us to a part where we did some part of the payload analysis already, but we reached a point where we're not able to progress any further. So NSO just hit a roadblock for us. Is this the end? Maybe, because there's a lot more to discover in this specific sample. We still have the home D crashes, where my initial assumption was that this has been another exploit chain. But Amnesty also found in their forensic investigation of the specific sample that there was also a call and an invitation. So maybe this is the first part of the chain. And we also have a couple of the other things not really accounted for. So where's the NS expression bypass? If there's another sandbox escape? Is there a pack bypass in all of those? Is our encrypted structure really the implant, or is there any other mentioning of a command and control structure that we haven't figured out yet? So what I can already tell you is the story for this sample is not over, and it's going to be continued. All right. Let's summarize what we did today. We started with a couple of MessagesBlastDoorService crashes, and those led us to investigate the backup. And in the backup, we found that at this particular point in time, there was an IM transfer agent process which was downloading a couple of iMessage attachments, which were our sample.pkpass files. If we investigated the sample.pkpass files, we found the logo.png, which was actually a WebP file, and it was not a PNG file. This contained a binary plist, and this binary plist is, if we de-archived it, contained an object at reference 11, which contained an NS expression, which then once again had a couple of different payloads. On the first payload, we had a reference to those payload CS, which contained a config file, and another reference to payload C, which then contained another of payloads subsequently, which we all decompressed. And then it contained another payload, and this other payload did have the reference finally to payload X, which is our encrypted sample. Now, this is already, it's a good starting point. Of course, the analysis is not done, but the great thing about this is we now have a couple of very interesting sample points where we can already have a couple of IOCs based on that. So the repeating MessagesBlastDoorService crashes are definitely an interesting sign, and they're definitely suspicious. It's not a clear IOC for the specific sample, but it's always worth investigating. The specific sample.pkpass file, it's definitely an IOC that you can easily check within MVT and automatically alert on. Then for a couple of times now, we have seen that attackers are using file extensions, but the actual file type is not matching those extensions. So once again, this is not a perfect indicator, but it's a good starting point for an investigation. Then if you look inside the plist, you will see all those A's. And this is also a very, very clear indicator. So even just taking those A's is probably a good starting point to just investigate this particular file a little bit further. And what I can tell you is if you ever find an iMessage attachment, which should be a picture which contains a couple of strings which are just called function, 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 this is most likely malicious. I haven't seen a single case where this is not true. So just taking those particular samples like the A's and the function, and if Apple would have just implemented a function of looking into any iMessage attachment, just trying to search for this and alerting on that, they probably could have found a lot of exploits already just by doing this, and it's probably not so much of a performance cost. And then, of course, we have seen the specific payloads, which are also very visible in clear text, even just by running strings on the sample, and those are very, very clear IOCs. All right, a courtesy slide. If one of you will ever get into the situation that you're receiving a specific Apple threat notification, or if you believe your iPhone is compromised and you want help in doing the analysis or even protecting you further, please contact us at info@iverify.io. Reach out to a couple of other sources like Amnesty International, CitizenLab, Access Now, or feel free to contact me directly on Twitter or on LinkedIn. Okay, what I want you to remember from this talk is iOS forensic investigation works, but we need much, much more scale. We are doing way too less forensic investigations on particular sample, which is an advantage for attackers. And then also, if we're looking at iOS vulnerability mitigation, such as the mitigation iOS 15.1, Those mitigations are just bypassed with even more vulnerabilities. So I'm not completely sure if this approach is always going to be the best in trying to tackle the specific problems of mercenary spyware. And what we could also see here is that spyware vendors tend to reuse very, very complex exploitation frameworks. So there's a very high upfront cost in developing those, but if you can just reuse those over time, this makes the whole exploitation process a lot easier for them. But it also makes it a lot better for us as defenders, because then if we can find the same pattern of behavior again, and now if we just search for every NS expression inside of an iMessage attachment, we have a very, very good starting point for an analysis. Thank you very much for listening to me today. And now we have a couple of minutes left if you have any questions. Yes, please. Yes, so the question was if we know if the sample executed correctly. I honestly can't tell you. I tried executing the sample on my own, and I observed that there was at least a couple of those crashes which were resulting as well. But I also observed that there was a couple of behavior on my phone. But I couldn't really tell you if this sample executed correctly or not, because we probably missed the first stage of the exploit that set up the stage correctly for this NS expression. Yes? Yes. So the question was how much time did it take me to do the work of decompressing those NS expressions? One of the first roadblocks, of course, was this cut decompression, which took me a couple of days to figure this out. And then I probably spent 2 or 3 weeks, like in full, of trying to get a very first understanding of this one. And then I unfortunately had to stop, but the investigation is still continuing. Yeah, so the question was, we haven't seen it for the first time that attackers use NS expressions and people are trying to do the tedious work of decompressing it. And if it would be good to develop a framework or a tool to do this, yeah, absolutely. I started doing this a very little bit on myself, and maybe it's time to release some of that and try to do it in a more general approach. But I also know that I think Ian Beer already did that himself, so maybe we just try to reach out if we can like disclose a tool for that or like make it open source. The question was if I know the mechanism that triggered the execution of the NS expression in this particular case. No, this is still an open question to me, but I very much have hope that Ian is going to disclose more about this in his talks that is upcoming.
Does this work? Okay. Thank you for the excellent talk. I really enjoyed it. Quick question about like you show like multiple layers of compression and encoding. What's the logical explanation? Like, why do they need so many layers? Are those different components glued together, or what's the purpose, or just to complicate your life?
I have no clue about this one. So if you look at it, you will see that there's a couple of ternary operators, which essentially are like if clauses. And you can see that the sample is trying to calculate also how long it took to calculate certain things, and if some of the parts before that are ready or not. Maybe it's because they chained together certain elements and built that in like an exploitation framework, or maybe they just wanted to make the work of exploit researchers harder. I don't really know at the moment.
So if they change together, that means that probably on every level they have multiple other components to be chained alternatively. So that just gives a bit of scale of their other capabilities. Is that what you're saying?
Yeah. So what it looks like that this is pretty much very modular in state. So you have a phase where you have this config file which is used. Then you have another phase where you check if the config is actually existing, and if it doesn't exist, then you're just you're exiting and you're not executing anymore. And you're also having a phase where you're then loading like the additional encrypted payload. And I've also seen that they're doing XPC communication to other processes, even though we haven't fully figured this out yet. So it's definitely a very, very modular approach.
All right, thank you very much.
All right, I think we're at the end. Once again, thank you very much to listen to me, and I do hope you will have a wonderful Black Hat.